Okay, I hope you're enjoying this lecture series. I could have done it in a much better way through PowerPoint, but as a professor, I always have felt that when I stand here with this in my hand, this horrible little whiteboard before you, uh, I'm looking at you, you're looking at me, and I'm not reading any book, I'm not doing anything, I'm just telling you the way things are, and that increases our confidence and it tells us what we're doing. Okay, so in the first diffusion equation, remember we had ODEs. In the second, the neutron transfer equation, we had an integral differential equation. Now I'm going to talk to you about the integral equation. Now, if you integrate the integral differential equation, then can you write something like P is again the phase space. Chi P is something happening somewhere else, integrated over that somewhere else, plus some direct contribution. Now look at this simple, elegant, beautiful equation. It says that a quantity which, let me just define this as the collision density. Now collision density is, by definition, it is sigma t times phi, the total cross section multiplied by the flux. When you integrate this over the volume, you get the total number of interactions per cubic centimeter per second, integrate over volume. So it gives you the rate of interactions. So let's write this for the collision density and look what you have. So basically, for some phase space P that I'm interested in and some phase space P prime, from where I'm getting the contribution from something that happened over here, plus I'm getting a direct contribution, direct here as P. For example, in this room, if I put on a heater, so the heater is the direct source. P prime would be the heat coming from some other place. So this tells you that the collision density in phase space P is the direct contribution plus the indirect contribution. The indirect contribution means the collisions taking place in P prime which undergo a transition from P prime to P. So we're going to call K the transition kernel. The transition kernel K tells us that what is the transition from P prime to P. Now, P has 7 variables, so it's not something which I can just write for you straight away. But it's conceptually very simple, but when you do it, it looks difficult, but when you get into it and you are determined to do it, then you find that you can do it. And not only can you solve this, but you can do better things with it, such as optimization. But that's another story. Let's leave that for another lecture. Right now, what we have is the integral equation. Now, there were people before the Manhattan Project who had written the integral equation. There were Volterra, there's the Volterra equation, there's the Fredholm integral equation of the first kind, of the second kind, and there are so many ways of solving them. There are successive approximations, there is the Neumann series. And what I want to talk to you about is the Neumann series solution. Now, Neumann series solution says that, remember that random walk I was talking to you about? So now if you have two walls, some particles can just go across without a collision. Some would have one collision, then go across. Some might have two, then go across. Some might have three, then go across. Now, there are an infinite number of such possibilities. Each type of event has a probability, and the distance between collisions, when you sum it up over all these, should give you a characteristic distance of the problem that you're trying to solve. And that is exactly the problem we are trying to solve. We are trying to solve for the flux. In other words, we're trying to find the distance traveled by particles between collisions. Because between collisions, what's going to happen is that they're going to change the energy and angle and be transported in space. So I'm going to show you, I'm going to break this down into two operators, the collision operator and the transport operator. So I'm going to write K as an operator as C dot T, a collision operator dotted with a transport operator. And I'll show you what a beautiful structure it has. So conceptually, just right now to keep it very, very simple, to introduce the concept to you, that these are the various possibilities that particles can undergo. There was a mathematician called Poisson, and he wrote down the distribution function for this, and it's absolutely amazing how we can also arrive at that. And when I was doing my PhD well over 30 years ago, then that was one of the things I tried, and I tried to see whether he was right. And so I was making my own discoveries in those days. And so it's a beautiful piece of simple mathematical formulation that you have to do yourself. But first, it's the picture in the mind which I'm trying to make. So this is the integral equation. We solve it via the Neumann series, which has got to converge. And the Neumann series says that the flux is actually a sum of the fluxes for all the possibilities of no collision to an infinite number of collisions. And when you do that, then that is the Monte Carlo method of simulation. So huge computers. In the next lecture, I'm going to write a flow chart for you to show you how we are going to do it. Now, there's standard terminology in this. There's combinatorial geometry, how you define 3D rooms by first order surfaces, which means planes, second order surfaces, which means spheres, third order surfaces, which are cubic surfaces, ellipsoids, hyperboloids, fourth order surfaces, which are quartic surfaces, such as donuts, which is a torus. And you can define any part of space by the union and intersection and complement operators, the Boolean operators. So you can construct combinatorial geometry, you can tell a particle where he is, you can actually define 3D geometry, which I could not show you with diffusion equation and definitely not with the transport equation. So Ludwig Boltzmann, fantastic person, but he could never solve his own equations. So when you make an equation, of course, you would like to solve it. The transport equation cannot be solved. So you have to resort to numerical methods such as discrete ordinates, spherical harmonics. These days, so many newer techniques, but I'm not a deterministic person, I'm a stochastic person. So this is the method I grew up with over the last 35 years, and I even use it for optimization. So this is what I'm going to develop a little bit more with you, and then finally we're going to discuss all three. Now remember, the purpose of these lectures, actually we're not solving the integral equation here, it's like solving it. We are doing computer simulation, decision making. And so here it's just to make a picture in your mind that there's a diffusion picture, there's the transport picture, and there's the stochastic Monte Carlo picture. So till next lecture, that's all for now. Thank you.